Hi, this is Roxanne with ChemTalk, and in this experiment, we throw pure sodium into water. We'll show you why sodium is so reactive and the mechanism that really causes this explosion. Because, big hint, what scientists thought for a long time was wrong. So stay with us to explore the crazy, awesome world of chemistry as we unravel the mysteries of sodium, its reactivity, and the real reason why it explodes. Sodium is a group 1 alkali metal. All alkali metals are highly reactive, so they are stored in oil to reduce reactivity. Elements react with one another by gaining, losing, or sharing valence electrons to become stable like noble gases. Alkali metals only need to lose one valence electron to become stable, so this makes them highly reactive. Group 2 alkali earth metals need to lose 2 electrons to become stable, so they are less reactive than Group 1. Reactivity also increases as you go down a group. So lithium is less reactive than sodium, and sodium is less reactive than potassium. You can check out our other videos on lithium and potassium to compare their reactivity. The reactivity of metals increases as you go down a group, because their atomic radii increases as we go down the group. The positive protons in the nucleus attract the negative electrons, pulling them closer to the center. The electrons in sodium are further away than lithium. And as a result, the positive protons cannot hold onto the outer electrons as easily. So the valence electron in sodium is removed more easily than lithium, making sodium more reactive. In this experiment, sodium reacts with water to form sodium hydroxide and hydrogen gas. Sodium is more reactive than hydrogen atoms on the water molecule, so sodium will replace one of the hydrogen atoms to form sodium hydroxide. Sodium is able to transfer or lose its electron to the oxygen atom to form the ionic bond, sodium hydroxide. The hydrogen atom is removed and forced to take its electron with it. However, a hydrogen atom with one electron is very reactive, so it will bond with another hydrogen atom with one valence electron to form hydrogen gas. Sodium compounds such as sodium chloride or table salt are very common in our society and are relatively stable. However, sodium metal in its pure form reacts very, very violently with water. Sodium also has a tendency to react with the water in your body and can cause some very bad chemical burns. Remember how we told you earlier that we store sodium in oil? This is why. Sodium is very dangerous, so don't do this experiment at home. This experiment takes place over 3 stages. First, we added a few small samples of sodium into a large tank and checked the pH before and after the reaction. Next, we repeated this process but added a few smaller samples of sodium into a frying pan. Finally, we threw larger samples of sodium into a private lake. Let's see what happens in each of these scenarios, starting with testing small samples of sodium in the tank.
super high.
The pH scale is used to determine the acidity or basicity of a solution. The pH scale ranges from 0 to 14, and it expresses the concentration of hydrogen ions in a solution. The pH scale is logarithmic, so the increase or decrease of an integer changes the concentration of hydrogen ions by tenfold. For example, the pH of 3 is 10 times more acidic than the pH of 4. The pH scale is used to simplify such a wide range of values. Acids such as vinegar and citrus fruits produce hydrogen ions in water, so they have a high concentration of hydrogen ions. Bases such as detergent and bleach produce hydroxide ions in water and have low concentrations of hydrogen ions. Acids have a pH less than 7, and bases have a pH greater than 7. Neutral substances such as pure water have a pH of exactly 7. In this experiment, the pH of water before the addition of sodium was close to 7. This is what we would expect the pH of water to be. However, after the addition of sodium, the pH increased. Let's re-examine the chemical equation to explain this pH increase. Sodium reacts with water to form sodium hydroxide and hydrogen gas. Sodium hydroxide is a base because it produces hydroxide ions in water. The hydroxide ions can react with any hydrogen ions in the solution to form water. As a result, the concentration of hydrogen ions decreases, which increases the pH.
Got a little bit bigger piece. Won't be a big one.
Earlier, we explained why sodium is so reactive. But how and why does sodium explode in water? The long-held assumption was that hydrogen gas caused this exploding phenomenon. Hydrogen gas is highly flammable, so it would make sense that this is the primary cause for the explosion. However, chemists working at the Academy of Sciences of the Czech Republic in Prague were not satisfied with this explanation. They wanted to know why the hydrogen gas wouldn't just smother and stop the reaction from occurring any further. Philip Mason and Pavel Youngworth filmed this explosion using a camera that could take 30,000 images per second. From this footage, they observed the metal's smooth surface became spiky. The chemists concluded that the spikes were due to the positively charged surface of the metal. When the metal loses electrons to water, the atoms become positive. These positive species then repel one another to form the spikes. It was also clear that the spikes form faster than the production of gas. As a result, these unique spikes increase the surface area, which in turn increases the rate of the reaction. More hydrogen gas is able to build up due to the increased surface area, and a greater explosion thus occurs. Due to the breakup of the charged species, this phenomenon is now considered a Coulomb explosion. This is a great example of how the skeptical attributes of scientists help to improve our understanding of the world. We have a better understanding of how and why alkali metals explode in water. But why did the sodium metal not explode initially in the tank? Consider factors that could influence the explosion and post your ideas in the comments below. Thanks for watching this ChemTalk original. If this video was helpful, then like and subscribe below. For more chemistry resources, check out our website at www.chemistrytalk.org. Feed your algorithm more science education data points by following us on Instagram, TikTok, Twitter, and Facebook. Chem talk to you later.